Okay. Thank you for the kind introduction. It's obviously a challenging day, especially in your part of the world. We hope that the events there don't cast a sad pale on how medicine will proceed. And, it's sad when those sorts of social events limit what the potential is, and result in death when, our focus in medicine is to improve the quality of lives and the length of lives for others. And so that's going to be a lot of the discussion today is how can we use technology to make things better? I do have disclosures. There's one part where I'll mention it, although I don't directly talk about a product that we produce. So my hope is that by the end of this talk, you'll learn about the current technology and the capabilities of deep learning applied to imaging, but also other things in medicine, that you'll understand the strengths and weaknesses of deep learning as they're applied to medicine, and then assess the potential for AI to improve how we can care for patients. So everybody in the world today interacts with AI, whether it's the self-driving cars, the self-driving robots, or zombies that are walking through the cars, the fast financial markets and trading, which is what that left middle panel is about, and of course us in medicine, and the advances are tremendous. And there's a lot of excitement around AI. Now, there was also a lot of excitement around AI back when I was a kid, back in the 1960s. And, when I would watch TV and watch Robbie the Robot, I was convinced that by the time I was into my 50s, I'd be laying on a couch, a robot would be feeding me grapes as I just, watch TV or watch movies, who knows what. All the work would be done by robots. Last time I checked, that didn't happen. And in fact, in the 1970s, there was this so-called AI winter because there was a lot of disappointment in the fact that AI wasn't accomplishing the many things we expected. In the 1980s and 90s, there was the development of machine learning, which is a component of artificial intelligence where you essentially give a bunch of examples, data to a machine, and it figures out the pattern. And then in the last decade, deep learning has come on, and this is where you can give even more examples and it can find even more subtle patterns in that data. And so really it's deep learning that has caused the revolution and the excitement about artificial intelligence. And in fact, there's so much excitement that one of the fathers of this, a guy named Geoffrey Hinton, said that I think that if you work as a radiologist, you're like Wile E. Coyote in the cartoon. You're already over the edge of the cliff, but you haven't yet looked down. There's no ground underneath. It's just completely obvious that in 5 years, deep learning is going to do better than radiologists. And he said that back in 2017. So according to my calendar, I have about 37 days of life left in my career. Now, actually, that hasn't happened. I don't think that's going to happen. And in fact, he even admitted that it's not going to happen. Things are just a lot more complex than they appreciated. But why was there all this hype? Geoffrey Hinton is a smart guy. Why would he make such an ambitious statement? So there's an international challenge called the ImageNet Challenge, where people are given a bunch of images, about 1 million images. There are about 1,000 images of 1,000 different kinds of things. So like cats and dogs and planes and trains and so on. And people would develop algorithms to try to figure out what were in those images. There was a separate holdout set also of planes and trains, and they would try to build an algorithm that would figure it out. And if they got, into the 70% range, they were doing really good. But then in 2012, a deep learning algorithm came on the scene, and you can see suddenly there was a huge jump in performance. And the following year, another huge jump and another huge jump. And actually, one of the guys who developed one of these winners said, I'd like to take that. I wonder what human level performance is like. And you can see that he took that test and got about 95% right. Now, you can tell it's probably a little bit harder than planes and trains, but it will show, for instance, a piece of a wheel, or you have to know the genus and species of a flower or a tree or something like that. So that's why it's a lot more challenging. But the point is that computers were able to do better than humans by somewhere around 2014, 2015. And if the perception is that radiologists look at a picture and figure out the thing in it, then yeah, you could understand why he might make that prediction. But of course, radiology is much more complex than that. There are lots of things in the images, some of which are important, some of which aren't. Sometimes you have to put multiple findings together to make a diagnosis, or sometimes you have to be able to look through artifacts. But the point is that deep learning got really good. And in fact, they don't do this challenge anymore because the difference in the performance of these algorithms was so small that it was basically meaningless. But this is why there's so much excitement about AI. If you look at the number of publications that have these terms in them on PubMed, you can see this exponential rise. And so, for instance, in 2021, there were about 15,000 publications that included this terminology compared to, less than a couple hundred in 2015. So what is it about deep learning? Why is there so much excitement about it? Well, the big thing is that deep learning finds features and the weights, as opposed to conventional machine learning, where you had to do something to manipulate the raw data to expose a feature. So what is a feature? A feature could be something like the brightness, could be how sharp the edges are. In the case of things like, say, mammography, you look for microcalcification. So you look for a sudden change in the intensity where it becomes very bright. And so we would have to process the images to create features, and then the machine learning would figure out the combination of those features that would make a good prediction. So that meant that we both had to know how to calculate the features, but it also meant that we had to know what the features were. And so with deep learning, you basically just provide the image and the answer, and it figures out both the features and the weighting. And so that's a big difference. It can really optimize how to calculate the features as well as the appropriate weighting. So this is a little bit different look on how that works. So the typical deep learning model that we use is a convolutional neural network, and it gets its name because it's a mixture of convolutions and pools. So convolutions think of it essentially being like a mathematical lock and key. You put a matrix of mathematical values and you slide it across and you multiply the corresponding pixels in the image. So that's convolution. And when that mathematical matrix matches the image well, you're going to get a bright or a high intensity response. And so that's what the bright pixels here are, is some kernel found something that was interesting. In this case, it's mostly edges, lines, circles. And then pooling reduces the resolution. So essentially, a fixed size kernel can start to look at a bigger part of the image. And so now these lines and circles start to form things like eyeballs or noses or nostrils or mouths. And then if you continue to do these convolutions and pools, you start to get entire faces. And now you can start to recognize who is in the picture. And finally, at the end, then you do the traditional neural network with all the interconnected nodes and make a prediction. So this is the basic technology of deep learning. I know you're all disappointed that I don't have a lot of integrals and lots of mathematical formulas, but the fact is you can understand this conceptually, and that's all the more that I'm going to go into the technology of deep learning. Instead, I want us to think now about the clinical applications, and there are four basic categories. One is regression. So this is essentially giving me a continuous variable output, a floating point numbers, for instance, predicting the age from an image. The second task category is segmentation. This is where you assign a label to every pixel in an image, and that then lets you do things like measurements or further classifications, which is the third category. Classification, this is what catches all the attention. It, for instance, would make a diagnosis of this is normal or abnormal, or this is multiple sclerosis versus a brain tumor. And so deciding what type of thing it is classification. And then the fourth category doesn't really fit with the others, but they are around workflow and efficiency. So let's dive into those and understand a little bit more. So deep learning for regression, one of the earliest applications was bone age, which might seem a little bit weird. The reason is that a bone age is done for a very specific reason, and so it's got a very stereotypical report. Basically, we say the chronological age is, 4.7 years, but the bone age is 3.2 years or whatever the number. And so it's very easy for us to create a large database. And that's what drives deep learning. You got to have large numbers of cases. And because of that stereotypical report, we could generate it easy. Since that time, we've built algorithms that, for instance, can predict the brain age off of an MRI. So this is a standard T1 weighted MRI, and you can see the predicted age versus the actual age of the patient. And of course, what's interesting is not that we can predict that a 67-year-old is 67, but rather these outliers. Why does their brain look like it's 67 when they're actually 54? Or maybe it looks like 67 and they're actually 87, right? Those are the interesting things that we need to understand. And it also can be done with things like photographs, where you can predict the age of the person based on a photograph. And you know, again, it gets to the fact that sometimes we see patients that look like they're 50 when they're actually 30, or they look like they're 50 when they're actually 70. And you know, that has important implications for how aggressive and how we think about patients. Okay, segmentation. So this is labeling pixels in an image. And you can see, you know, we can identify the gyri on a brain or the liver in a CT. And this allows us to do various types of measurements. For instance, we can measure the size of tumors. We can measure it volumetrically. We can also identify structures like radiation treatment plans and say, you know, maximize the dose to the tumor, but try to avoid the cord. And without having those outlines to put into the treatment plan, you're not going to come up with a very good treatment plan. We can also do things like body composition, which is the measurement of not just of the amount of fat, but also the distribution of fat, whether it's subcutaneous or visceral, has been shown to have important impacts on the patient. Also, the amount of muscle that in the abdominal wall kind of reflects how robust a person is. And so this is now a tool we have in clinical practice here, and it's used for clinical planning, essentially how aggressive might you want to be. A lot of drugs are dissolved into fat, so if you have a lot of fat, that may affect how you do dosing. And of course, counseling as well, right? If you have a patient who really has strong numbers, a lot of patients listen to the numbers a lot more than they listen to doctors. And so counseling how they have to change their lifestyle could also be impacted by this technology. So the third class then is deep learning for classification. And again, this basically says, is a disease present or not? Is it disease X or Y? Is it progression or response? So essentially it's defining categories and putting you know, an image or a patient into one of these other categories. So for instance, a common task is to read chest x-rays, and this was developed from a large database, over 100,000 chest x-rays from almost 40,000 patients. And what they found is that an AI tool could work essentially as well as a radiologist. And here are the ROC curves for the different categories of findings. And the point here is that while there was a difference, the difference was not statistically significant. So the AI was basically as good for everything except emphysema. And emphysema actually probably was a labeling issue in that the training data was not reflective of the actual population. Some of the work out of my lab, we take brain MRIs of patients with gliomas, and we can now predict important molecular markers with pretty high accuracy. So IDH1 essentially tells you whether or not it's a glioblastoma. If it's not IDH wild type, if it's a mutant, then we look at 1p19q chromosomal, and if they're co-deleted, then that basically means it's an oligodendroglioma. Other things like MT methylation is a good indicator of whether or not the traditional things like radiation and alkylating agents will be effective. If it's not methylated, then you probably want to look at other agents. But you can see we're actually quite accurate at predicting these from routine T2 weighted images. And this was a multi-institutional study. There's no segmentation, so there's no human step involved. So this is another tool now that we're rolling out into practice here. This isn't just for radiology. I'm a radiologist, so that's what I have focused on. But it can be used, for instance, with pathology images. And again, there's a lot of tedium in looking at every bit of a slide of every bit of a tumor, and having a computer that can go through and find the interesting parts on a slide, and then actually start to, again, predict molecular markers from standard H&E stains can be valuable because it can give you a good indication early rather than having to wait days or weeks for a molecular marker test to come back. Pap smear is another task that computers can do at least as good, if not better than humans. So AI is impacting all of medicine: pathology, cardiology, dermatology, oncology, even palliative medicine and psychiatry are having a value from artificial intelligence. So no matter what specialty you go into, you will be working with AI in the future. Now, that sounds really exciting, but there are some concerning areas. First of all, does AI always find the right features? Remember, I told you how deep learning works, that basically you give the data and it figures out the answer, and you don't control the features necessarily. And so the AI is going to find the features that produce the best score on the examples provided. And so it's learning patterns, it's not intelligent. And so if the features make no sense, there's a problem. And also, if the numbers of examples is small or misleading, it can find spurious features. Let me give you an example of that. There are papers published in the literature where it was found later on that the signal or the feature that was used to help make a prediction was totally irrelevant. In one case with mammography, it looked at the marker, and in one case they had to have a increased number of breast cancer cases, so they went to a non-screening setting, and the AI found that marker that said, these are non-screening patients, these are going to be cancers. So it was totally irrelevant. It's not something that we could use in the real world, but without careful attention to what the AI is looking at, it came up with a misleading and over promising what the results would be. There are also concerns about how susceptible it is to noise. So here's an example. If you look at the image on the left, that looks like a panda, right? But if you carefully engineer and add just the right type of noise, and this looks like random noise, right? It's not random. It is very carefully engineered noise. And what they found is that by adding this to this panda image, they get this image. But now the AI tells us this is a gibbon with 99.3% confidence. Okay, so the problem is that the AI learns features, something about the examples that it saw of panda, and by playing with the right pixels, it can totally throw off the prediction. We can use that in real life. You know, we have some self-driving cars that try to read stop signs, but what some people found is that by putting these black and white markers on a stop sign, the car would no longer recognize it as a stop sign. That's not good. If you're concerned about surveillance, you know, we have these tools that will identify, this is a person in the surveillance video. But they found that by doing something like hanging this picture of a crowd here, it would not recognize this as a person. Okay, so AI is not smart. Any one of us would recognize both of these individuals as being individuals, or this is a stop sign. Generalization can be a problem. Oh, kind of like the spy versus spy, where everybody keeps one-upping each other. People figured out how to use this for an advantage. And so we have a technology called a generative adversarial network, or GAN, that will actually start to generate new examples of images. So for instance, there's this website called thispersondoesnotexist.com. This is actually a totally synthetic image. This person does not exist. You may know somebody who looks a lot like it, but it was purely synthetic. And in fact, you can do it to video frames too, where you can match the words and generate a face that will look like they're saying the words. We can use this in medicine too. So for instance, we can use much lower doses of gadolinium on MRI scans, and these GANs can generate images that look just like the full dose was there. We can also generate, for instance, CT scans from MRs. Why would you want to do that? Well, in many cases, an MRI will show a tumor much better than a CT, but a CT is needed for treatment planning. And so if you can generate a CT from the MR, you can do the treatment planning and it's perfectly aligned so you don't have the inaccuracies of planning. In some cases, tools need all the different MR pulse sequences, but not always were they acquired, particularly in the past. So we built a tool that would generate missing pulse sequences to satisfy subsequent AI tools that wanted these other sequences. So it's amazing what GANs can do. Now, hopefully you're starting to have some concern about whether AI is really trustable. Is it really something valuable? And you've probably seen things like this. These are called saliency maps. So it turns bright red where it says, this is what I'm really looking at. And that's nice, but why does why does the neck light up? And also sometimes it's not so much about where it is, but it's more what it is, right? So textures or intensities can be important. And if the AI doesn't explain what it is, then knowing where it is not necessarily so great. So for instance, here we have built a lot of tools for diagnosing COVID. And this tells us where the pneumonia is, but hey, we all know pneumonia is in the lungs, right? Why is this COVID rather than some other type of pneumonia? And so these saliency techniques do not solve that problem. And we don't have a great tool yet for explaining textures, so to speak. And so trusting in AI is a problem where tasks where the focus is efficiency, like doing segmentation, trusting AI is usually pretty easy. You can look at it and say, yeah, I agree with where it defined those boundaries. But for tasks where AI finds something that's not visible, like predicting those molecular markers on AI, we're basically going to have to trust but verify, right? We'll trust that it got it right. We'll behave that way, but then we're going to go back and look to see, did it really get it right in the long term? And I think this is where one of our former presidents, Ronald Reagan said, trust but verify. And I think that that's appropriate for us in medicine today too. Okay, so if we're going to trust these, we first of all need to look at what the data sources were, and we need to question, was the training data sufficiently diverse? In particular, things like race have become a big issue, and it turns out that even though we human observers may not be able to clearly identify race from radiological images, it turns out that AI can. And in fact, this was a really interesting study done by some friends of mine where they took a collection of several different images, including things like chest x-rays, but also mammograms and CTs, and they could predict the race and gender from these images with very high accuracy. And even after they did a lot of damage to the images, for instance, they would reduce the resolution, they would reduce the grayscale, they would still be better than 90% accurate at predicting this. And that even includes things like a mammogram. Can you imagine how you could tell the race of a person from a mammogram? If you've looked at many of them, I think that's a pretty impressive task. And same things with chest x-rays. So there's a lot of information there that we don't perceive. Why is that important? Well, if you build an AI tool from a population that's, say, mostly Caucasian, and then you say, oh yeah, go ahead and use this in, a population that doesn't have many Caucasians, the AI may well have used some of the Caucasian type features in order to make its prediction, and it may start to become quite inaccurate for predicting in different races. Kind of like the example where mammograms, it was looking at the marker saying, this is a breast cancer clinic, rather than looking at the real content that's relevant for a diagnosis. And so their conclusion is that we demonstrate that medical AI systems can easily learn to recognize racial identity in medical images. Furthermore, they then recommend that if you're doing medical image analysis, you should consider the use of deep learning models with extreme caution. And finally, down that last red point, explicit model performance audits should be based on racial identity, sex, and age. So you need to look at what the distribution of your data is, make sure that it's relatively diverse, and that it is relatively similar to where you intend to deploy it. There are also concerns about AI and privacy. It turns out that, for instance, retinal images but also it turns out that the venous pattern on the back of your hand is highly individual. While we humans, again, are not that good at picking up on these patterns, they can figure out things like the age of the patient, the gender of the patient, the hemoglobin, systolic blood pressure, and so on from a retinal image. And it kind of goes to if you have ever gone through the airport and used that clear system where they look at your eyeballs to determine who you are. These are highly individual, and so we have to be very careful that the AI isn't starting to identify who a person is. And in particular, that if we're starting to build these large databases, we also make sure that we are appropriately careful in how that data is passed around. So, when we think about what is AI, of course, we know AI is artificial intelligence, but I think that it also has an alarming level of identification of specific people and or populations. I think there's also the potential for amazing individualization where we can start to recognize molecular markers very well from routine imaging, and that's going to enable us to personalize the care of patients much better than we ever could in the past. So AI is not a purely good thing or a purely bad thing. It all comes down to how you implement it and that you need to be attentive to the potential problems that it introduces. Finally, I'll talk now a little bit about AI for workflow and efficiency. Deep learning is already dramatically impacting medical imaging. It gives us faster and better image acquisition. You may not know it, but already a number of MR and CT scanners have this technology built in. It goes under several different names, but basically you can acquire much less data, whether it's less dose in the case of CT or less time in the case of MR. And the deep learning is able to reconstruct images that look every bit as good as the full dose, full time image that we would normally acquire. And so we're going to be able to do a much better job than we could ever do before. AI can also do a lot of human tasks, whether that's things like splitting up the exams, sorting things, sorting data, naming things, kind of the routine stuff that we face in a lot of medicine. We can just do better with AI. It will be higher quality and it will be more efficient. There are also people who are looking at how we can start to use AI to combine all the test results for the optimal care of the patient. So this was a nice diagram out of the group at Harvard where they, have a patient and they look at the care stream for a cancer patient and the various steps that are involved and how you need to synthesize all this information. And while human doctors try to do this, the fact is there's so much information and sometimes you're not aware that this test result came in or you didn't know that this other hospital had done this test. AI can help pull all of it together and can also help to do a reasonable first pass interpretation of what all that information means. So that's a really pretty picture. And so the dream then for AI implementation is kind of like the Emerald City, where it's going to be this golden path. We're just going to pull all this information in and everything's going to be hunky-dory. The fact is, it's a lot more challenging than that. Getting information and how that information is represented has always been a challenge with EMRs, and AI is only amplifying that challenge. So now I want to turn a little bit historic and go back to the 1960s. And one of the original AI applications in medicine was actually just building a rule base. And it was about 500 rules, and the tool was called Mycin. It operated essentially at the level of human specialists in blood infections and better than general practitioners. And the program could request getting additional information saying, I need, this test result. And it could also recommend a course of treatment, put them on this kind of antibiotic. And if requested, it could also explain why it came to the diagnosis or recommendation that it came to. So, I think that this sort of technology has value because there's so much of an understanding that goes into how it came to recommendations, and that black box criticism of AI has a certain amount of validity. And so these sorts of technologies are really cool. Now, there is a modern form of it. It's called robotic or intelligent process automation. And so the idea here is that for medicine, I should say, these process automation tools are put into practice today for things like manufacturing or shipping and logistics. Even banking and credit card processing use IPA or RPA. Medicine has been really slow to adopt this, but I think that this is something that could have a great impact on us. So that the idea here is that there's going to be an ecosystem of various AI tools in the clinical environment, ones that work with different types of data, work on diagnosing different problems, and it's undesirable to have each doctor decide whether to run a certain AI tool, whether the information is present or not. All these logistics issues are important. And I think also that the information required by AI tools is going to increase in volume and complexity. So today, most of the AI tools we have just take a CT or an MR scan. But the reason that I think I can do better than most AIs today is because I can also integrate the patient gender, pathology results, all these other pieces of information that today's AI tools can't integrate. We will, and we are learning how to integrate non-pixel data with pixel data. And so the idea then is that these process automation tools will have predefined criteria that would determine the AIs and non-AI steps that should be applied to each patient care stream. And these would then be integrated using existing informatics standards, things like DICOM, HL7, FHIR, and so on. And these are going to be more cost-effective over the long term and probably also improve quality. And in fact, others would say this too. In fact, the quote here is that in the next decade, more than 50% of the interactions will be automated through RPA. This also means that healthcare providers that don't keep up with industry trends will face financial downfall. So RPA is starting to make its way into healthcare. It's basically where you set a number of rules or conditions and say, when you see this, do that, which is that, original form of AI in medicine called MYCIN. And I think this is actually going to have a big impact, and others agree. The cool thing too is that process automation can collect a lot of data along the way that can be valuable for training artificial intelligence to, again, replace humans where we don't need humans. If humans just always do a certain step when they see a certain condition, that can be automated. Let's let humans focus on the things that humans do best and let machines do what machines do best. So my prediction is that this process automation is going to have a bigger impact on the practice of medicine 5 years from now than deep learning. But after that, deep learning is going to start to take the lead. Now, of course, I am a little bit cautious. I saw the other person's prediction about 5 years in radiologists, and predicting the future is easy, being right is hard. I try to be right. I hope I'm right. And I think that we should at least be aware of this possibility. So I've mostly talked about images up to this point. I'm going to briefly talk about natural language processing. This is not my area of study, but it is making amazing advances. Deep learning have made incredible advances when you look at the technology behind, and I don't want to set off the names, so I won't say them here, but you know who they are, right? And also automated language translation. I just heard a statistic now that tools that are available like Google Translate can cover about 80% of the world's population fully automatically. And so that sort of technology I think is amazing too. And yet NLP in medicine is still limited. I'm doing radiology today. I'm reading out cases. And so I deal with speech recognition. Here's my speech recognition mic. And yet it's still it's not that great. It's 99%. That sounds great, right? But how many words are there in a report? Well, if there's, say, 200 words, that means there are 2 errors in each report. And that's just not good enough. And speech understanding in medicine is poor. And even we humans struggle with that, right? When you read somebody else's note that they've transcribed, do you fully understand everything that's said? No, we all have our special abbreviations. We have our special ways of expressing things. it's a hard problem. And so I think NLP, to really understand all the clinical notes and help make a diagnosis, is probably a ways off. I think that NLP probably will be more useful for the mundane tasks like patient scheduling, interacting with patients to understand, what are your symptoms, that sort of thing. Validation of indications or billing, gee, Mrs. Jones, did you really have this symptom? Did you feel this way? Billing, where you look at what was diagnosed and, does the bill seem to reflect that? That's 99% is probably good enough. So, as I start to wrap this up, this is a question that always gets asked, is AI going to replace me as a doctor? The old man versus medicine question. And a couple of you in the audience know, actually, my wife is a physician, and she says, that's the usual male ego. It's really about woman versus machine. And hopefully there are some giggles going on. The point is that it's not about human versus machine. It's about human versus human with a machine. There's just too much hype on computers replacing us. There's way more information, for instance, in images that computers can extract, whether it's the quantitative values from segmentation that are hard or painful to get at. There's a lot of unseen information. The molecular markers, I think that's incredible that there's information there. But we need to engage with AI scientists to make sure that the AI implementation is optimal for the care of patients, that it's not just an IT project. Andrew Ng, who's one of the major players in artificial intelligence, said that any task a human can figure out in 5 seconds can be done well by AI. And I think that that's a good rule of thumb when you think about, can AI do this or not? There are a lot of things that, we just instantly know what it is. That's probably something that AI can take off of our task list and give us time to think about the problems that we really do need to spend some time on. So you've probably seen the Gartner hype cycle, AI in medicine. We had this technology trigger where deep learning came on the scene, and it was going to be amazing. And then suddenly, we're saying deep learning can do anything, include replace radiologists. Now, I think we're starting to go down into this trough of disillusionment where we feel like deep learning can't do anything. And, it's biased, it's racist, it's, terrible. I think, in the 2024 to 25 range, we're going to start to recognize that deep learning can help, and that the challenge is how to efficiently integrate it into the care of patients. So the take-home points. AI is incredibly powerful, and the main limitation of what it can do is our imagination. How can we think of I wonder if AI could predict, X, Y, or Z. So, don't be shy about thinking imaginative thoughts about what AI might be able to do. Now, in some cases, though, we may not understand the power or the basis for a decision. Things like subtle textures or complex interplay of features, and that's a problem. And the features and predictions then, if they're not appropriate, can lead to unintended outcomes. So we have to be very careful, particularly at the start, to make sure that the AI really is behaving the way we think it should. And then finally, I think that mundane AI, such as process automation, actually may be more important for the immediate future, the next 5 years or so. So thank you so much for your attention. I think we have a little bit of time now for questions from the audience, and I'd be happy to do my best to try to answer them. Thanks.